String theory is the most potent and powerful approach that we have discovered as a species for blending general relativity and quantum mechanics.
What if two of the most popular ideas in modern cosmology are built on shaky ground? One of the world's most respected physicists thinks so, and he is not subtle about it.
The theory, to me, is just in the wrong direction, and it's wasting a lot of time.
I, like many string theorists, think that we live once. I'm not interested in spending my time on a theory that's wrong.
The trouble is that they claim it's such a beautiful theory. As far as I can see, it's a great mess.
But for two theories that were at loggerheads to naturally come together where one induces the other to emerge from the formulation, that's beautiful.
Roger Penrose is not timid when he points out what he sees as serious problems with string theory. He does not call it bad science in a whisper. He says the theory rests on assumptions that have not been proven, and that many of its most dramatic claims cannot be checked by experiment. That is a sharp charge coming from a mathematician who helped build modern gravity theory. It is worth taking his point seriously, whether you end up agreeing or not.
Well, I think the trouble with string theory is that there isn't any connection with observations. As far as I'm probably taking too strong a view here, but the mathematics, it's largely driven by the mathematics as far as I know, which is in itself is not an objection as far as I'm concerned. A lot of what I do is driven by the mathematics. But the trouble with string theory is it's supposed to be a theory of the way the world operates. And if the number of dimensions of space is just wrong, I can't take it seriously. If you could have a theory which had predictions, and these predictions could be seen to be right or wrong, that's what I understand about physics. But string theory seems to me driven largely by certain ideas which have importance in mathematics, but sort of irrelevant to the physics, really. As far as I know, there's places where string theory has had an impact on mathematics. Sure, it has, but it's not physics, as far as I can see. So the main trouble I have with string theory is I don't think it's physics.
First, a quick note on what string theory tries to do. At heart, it aims to unify gravity with the other basic forces by replacing point particles with tiny vibrating strings. Different vibration patterns would show up as different particles. To make the math work neatly, string theory typically needs more space dimensions than the 4 we experience. That is one of the main places Penrose starts to push back. He argues that adding extra dimensions is not a small tweak. It is a radical hypothesis built to rescue a calculation rather than a step grounded in measurement. In his book and lectures, he says this move is more like mathematical fashion than a move grounded in physical evidence. When a theory requires entire invisible dimensions, we should expect very clear predictions that follow from that assumption. String theory, he argues, has not delivered those clear testable predictions in a way that counts as real experimental support. To understand why extra dimensions are a serious issue, imagine you wanted to explain why a radio plays music. One idea says radios work because of known electromagnetic waves and circuits. Another idea says there are also hidden rooms inside the radio where tiny musicians live, and their dances produce the music.
She's only a bird.
That second idea might be logically consistent, but if it adds whole new kinds of objects that you can never observe, then it is hard to treat it like physics rather than poetry. Penrose's point is similar. Extra dimensions in string theory are introduced to satisfy internal consistency and symmetry requirements of the mathematics. They are not introduced because we saw direct signs of them in nature. That moves the theory away from the empirical heart of physics and toward a reliance on mathematical form alone. Penrose's second big point is about prediction and testability. Science rests on being able to test ideas, to rule some of them out, and keep the rest. A powerful theory must expose itself to experiments that might fail. Penrose believes string theory has become too tolerant of anything goes. One of the technical ways this shows up is the so-called landscape problem. Once you allow the many ways extra dimensions can be curled up, string theory appears to predict an enormous number of possible low-energy laws of physics. That means the theory can be made to match almost any observed values of constants by choosing an appropriate compactification. If a theory can fit a vast range of outcomes by adjusting hidden details, it stops being predictive in a useful way. Penrose sees this as a major methodological flaw. He worries that when a theory cannot point to a single clear outcome, it stops making risky bets and instead shelters itself from real falsification. Connected to this is the use of anthropic reasoning by some string theorists. The anthropic idea says that some features of the universe are what they are because otherwise observers like us would not exist to notice them. It can sometimes be a useful observation, but Penrose warns that leaning on such reasoning erodes explanatory power. If a theory explains why things are the way they are by saying they had to be this way for us to be here, then the theory can avoid offering deeper mechanistic reasons. For a healthy physics program, Penrose argues, you need mechanisms that link assumptions to measurements in clear ways. Invoking anthropic selection as a central justification, he believes, is a sign that the theory is out of contact with the kind of testing that makes physics a robust enterprise. Penrose also raises a mathematical concern he calls functional freedom. This idea focuses on the gap between a theory's formal structure and the concrete physical functions it must reproduce. In the case of string theory, the mathematics is very flexible. There is a large space of mathematical solutions or backgrounds, and many of these can be adapted to show properties similar to our universe. Penrose's complaint is that such flexibility weakens the theory's explanatory bite. If a mathematical framework can be tuned to produce almost any outcome, then the framework itself is not doing the heavy lifting of explanation. The heavy lifting falls to choices that are left free. A theory that explains less and permits more free choices is a theory that has moved away from control by evidence. Critics have debated whether Penrose's functional freedom argument proves the theory is wrong, but it highlights a real tension between mathematical breadth and physical constraint. Another strand in Penrose's critique looks at the social side of science. He warns that fashions in theoretical physics can gather momentum for reasons outside pure evidence. A promising mathematical structure, a well-funded community, and an appealing formal story can draw many researchers into the same lines of work. That concentration can push some other approaches to the margins. Penrose thinks that the string community's size and the long prestige associated with the subject may have slowed the adoption of alternative ideas that deserve serious study. He does not say that every person who works on strings is acting badly. Instead, he raises a caution. The sociology of science matters. When a discipline leans heavily on a fashionable idea, it can become harder for young researchers to pursue other productive paths. That vulnerability can slow progress, especially if the favored approach is not producing clear, testable results. Penrose also attacks a deeper assumption that lies behind much modern physics. He believes quantum mechanics, in the form we usually use it, is not the final word. This point is crucial because string theory accepts standard quantum mechanics as part of its framework. If the quantum framework needs revision, then any theory built on top of it deserves new scrutiny. Penrose has argued for a specific kind of change. He proposes that gravity may play a role in how quantum states collapse to definite outcomes. In standard quantum mechanics, systems can exist in superpositions until an observation causes collapse. Penrose suggests that very large or very massive superpositions are unstable and will undergo an objective collapse due to gravitational effects. This idea has a technical form in models sometimes called Diosy-Penrose proposals, and it leads to testable differences from standard quantum predictions in carefully designed experiments. Penrose thinks that facing up to these kinds of alternatives is important, rather than folding them into a framework that already assumes the standard quantum rules. That idea, the gravity-related collapse, also feeds into why Penrose thinks string theory's starting point might be wrong. Most versions of string theory rely on quantum field theory tools and quantization procedures that assume the standard rules of quantum mechanics. If those rules are not complete, or are only approximate, then the whole scaffolding needs to be re-examined. Penrose sees a need to consider new physics that addresses the measurement problem and the role of gravity. He has built alternative mathematical structures, like twistor theory, which aim to recast the basic building blocks in a different language that lives in 4 dimensions, rather than many unseen dimensions. Twistor theory rewrites points in spacetime as objects in a different mathematical space, where certain calculations become simpler. Penrose believes these approaches are, in principle, closer to what we can try to test and may avoid some of the conceptual traps he sees in string theory. There is also a plain practical argument Penrose makes. After decades of development, string theory has not produced a unique set of values that match our universe, and that could only be explained by string theory alone. No smoking gun prediction has emerged, no distinctive particle or effect that would force acceptance. By contrast, previous breakthroughs in physics gave concrete signals to look for and experiments that could settle debates. Penrose points out that a theory that keeps changing its explanations to fit what we already see is not behaving like the historical successful theories of physics. The risk is that theoretical elegance and mathematical depth are being used as stand-ins for empirical contact. Penrose treats mathematical beauty as a helpful guide, but not as a substitute for experiment. If mathematics becomes the final arbiter, he says, physics becomes a branch of mathematics, rather than a science driven by the natural world. String theorists have responses to these criticisms. They note that the theory has generated genuine mathematical advances and new calculation methods that have proven useful beyond the original aims. They also say that the lack of direct experimental data at the Planck scale is a practical barrier, not a conceptual failing of their approach. Some argue that progress in physics sometimes requires patient theoretical work before experiments catch up. Penrose accepts that mathematical advances are valuable, but he keeps asking whether the advances tie back to testable claims about the world. The two positions can coexist as a debate about priorities and tactics. Penrose says physics should not drift into speculation without firm experimental anchors. Proponents of string theory say that the math is building an infrastructure that may one day point to those anchors. The debate is less about personalities and more about what counts as legitimate progress in fundamental physics. It helps to put the disagreement into everyday terms. Suppose a mechanic builds a theory of cars by making a very powerful computer model with many adjustable parts. The model can reproduce any observed speed, fuel usage, and noise level simply by changing hidden knobs. The mechanic insists the model is correct because it is consistent and elegant. A critic says that if you can dial anything you want, the model does not help you predict how a new engine will behave on a cold morning. You still need a small, sharp test that shows the model makes risky predictions that could be wrong, and, if wrong, would require the mechanic to change the model. That testability is what Penrose is asking for in fundamental physics. He sees string theory as powerful, but too flexible to be held to the kinds of tests that have marked successful theories in the past. What about Penrose's alternatives? As noted, He promotes twister theory and objective collapse ideas, and he has proposed cosmological ideas that differ from mainstream inflationary accounts. Twister theory targets the mathematics of space-time itself. It rewrites events so that certain particle interactions become simpler. Penrose believes this four-dimensional approach avoids the need for extra dimensions. The objective collapse ideas suggest that gravity makes some quantum states collapse on its own, producing definite outcomes. Together, these proposals try to address both the technical and conceptual gaps Penrose sees in existing frameworks. He does not claim his roots are complete. He presents them partly to show that different testable paths exist and should be taken seriously in the debate about what fundamental physics should aim for. Many philosophers and physicists have taken up Penrose's arguments and discussed them in detail. Some defend string theory's potential and point to broader cultural and technical reasons for its dominance, such as the way it unites many separate threads of mathematics. Others say the real problem is not string theory itself, but the broader context. The lack of new experimental data at the highest energies and the social incentives that shape careers. Penrose's critique works best as a warning that we need to balance mathematical imagination with empirical testing. It is also a call to fund and study alternative approaches so that the field remains open to multiple ideas that could better match whatever future data arrives. In addition to his criticism of string theory, Roger Penrose has been just as blunt about cosmic inflation. He has repeatedly said that the standard inflationary story does not solve the problems it claims to solve and, in several ways, makes them worse. When he calls inflation nonsense, he is not trying to shock for attention. He is pointing to what he sees as deep logical and scientific weaknesses that are often ignored because inflation has become widely accepted. To understand his position, it helps to recall what inflation is meant to do. Inflation proposes that, very early in the universe's history, space expanded at an extremely fast rate for a very short time. This rapid expansion is supposed to explain why the universe looks smooth and uniform, why distant regions have similar temperatures, and why space appears close to geometrically flat. Many cosmologists treat inflation as almost settled fact. Penrose does not. He argues that inflation does not explain these features in a meaningful way. Instead, he believes it quietly assumes the very special conditions it claims to explain. Penrose's main objection begins with the idea of initial conditions. Inflation is often presented as a mechanism that makes the universe smooth and uniform, no matter how messy it started. Penrose says this is simply not true. For inflation to start at all, the universe must already be in an extremely special state. The inflation field, often called the inflaton, must be smooth over a large region, with very specific energy properties. That smoothness is not explained by inflation. It is assumed from the beginning. Penrose argues that this is like claiming a machine cleans dirty clothes, while quietly assuming the clothes were already almost clean before going into the machine. He goes further and says the required initial state for inflation is actually more special than the non-inflationary universe inflation was meant to fix. Using ideas from gravitational entropy, Penrose argues that the early universe had an extraordinarily low entropy state. This low entropy is tied to the smoothness of space and the absence of gravitational clumping. Inflation does not explain why the universe started in such a low entropy configuration. In Penrose's view, it hides the problem behind a new field and new assumptions, then claims victory without addressing the core issue. Another major point Penrose raises concerns probability. Inflationary models often claim that inflation is generic or likely. Penrose strongly disagrees. He argues that when you look at the full space of possible initial conditions allowed by general relativity, the conditions that lead to inflation are incredibly rare. they occupy a tiny fraction of what is mathematically possible. So instead of inflation being a natural outcome, it requires careful tuning. Penrose has used vivid numerical examples to show just how tiny this fraction is, numbers so extreme that they defy normal intuition. For him, calling such a scenario natural is misleading. Penrose is also skeptical of how inflation handles structure formation. Inflation is said to explain how tiny quantum fluctuations were stretched to cosmic scales and later became galaxies and clusters. Penrose points out that this explanation relies on unresolved issues in quantum theory itself. In standard inflation, quantum fluctuations somehow turn into classical density variations. But the mechanism for this transition is not clearly defined. Penrose connects this directly to his broader concern with quantum mechanics. He argues that without a real physical process that turns quantum possibilities into definite outcomes, inflation's explanation of cosmic structure rests on shaky ground. Related to this is his discomfort with how inflation treats randomness. Many inflationary models appeal to random quantum effects to explain why the universe looks the way it does. Penrose does not deny randomness plays a role in physics, but he insists that randomness alone cannot replace clear physical explanation. If the universe's large-scale features are explained by saying that is just how the fluctuations happened, then the theory is no longer giving deep understanding. It is only shifting mystery from one place to another. Penrose also criticizes the way inflation has multiplied into countless versions. There is not one inflation theory, but many, each with different fields, potentials, and assumptions. When one version runs into trouble, another is proposed. Penrose sees this as a warning sign. A strong scientific theory narrows possibilities. Inflation, in his view, keeps widening them. This flexibility allows inflation to survive almost any observational result, which weakens its scientific bite. Another point that troubles Penrose is eternal inflation. Some inflationary models suggest that inflation never fully stops and keeps producing new regions of space with different physical properties. This idea is often used to justify why our universe has the constants it does. Penrose finds this deeply unsatisfying. He sees it as closely tied to anthropic reasoning, which he believes avoids explanation rather than providing it. Saying our universe is this way because otherwise we would not be here does not tell us why the laws take the form they do. For Penrose, this is not physics in the traditional sense. It is a retreat from explanation. Penrose also objects to the historical narrative around inflation. Inflation is often described as a brilliant fix to several puzzles at once. He argues that this narrative exaggerates inflation's success. Problems like horizon uniformity and flatness are real, but Penrose believes they point to something deeper about the universe's initial state, not to a brief burst of rapid expansion. Inflation, in his view, distracts researchers from asking the harder and more fundamental question: why was the early universe so special to begin with? This leads directly to his alternative thinking. Penrose believes cosmology must take entropy and the arrow of time seriously from the start. He has proposed ideas like conformal cyclic cosmology, where the universe's far future is mathematically linked to a new beginning. Whether or not one accepts this model, it shows how Penrose approaches the problem differently. Instead of adding new fields and phases like inflation, he tries to explain cosmic order by deep geometric and thermodynamic principles. Penrose is aware that many cosmologists strongly disagree with him. They point to observational successes of inflation, such as the near uniformity of the cosmic microwave background and the spectrum of density fluctuations. Penrose does not deny these observations. He challenges the claim that inflation uniquely explains them. He argues that matching data is not enough if the theory relies on poorly justified assumptions and unresolved conceptual gaps. If you found this breakdown useful, let me know what you think in the comments. Do you agree with Penrose, or do you think inflation still makes sense? Your take really matters here. If you enjoy deep explanations like this, make sure to like the video and subscribe to the channel. It helps the channel grow and lets you know when the next video drops.